right. So, those were the points, maybe first set of points to be looked at from the data sheet itself. What we will now attempt to do is say that okay, we went through this from the data sheet, how do we now put this together in the form of a schematic, right, because now if I go back to what is an embedded system engineer's responsibilities, what an embedded system engineer has to do is chip selection and then integrate those selected chips onto the platform in the form of both hardware and firmware. So, the hardware representation is first level of representation is the schematic and then the physical representation is the layout. So, we first need to make a schematic of the battery charging subsystem with all of its connections. So, I have sort of already done that for you. So, I am just going to pull it up and walk through it, right. So, an example connection would look something like this. We do it for one of our products. So, you see some text that might not be necessarily directly relevant to you, and that is okay. But a schematic would look something like this. So, let us just work our way through the pins, right. We have the input pin. The input pin is connected to VUSB, which is the supply. The ISET pin is connected to a 680 ohm resistor, right. So, let us try to, if you remember, ISET is equal to K ISET divided by R ISET, right. This is 540 ohm ampere divided by R ISET, which is in our case 680 ohms, right. This is about 800 milliamps of current, right. In our application we decided to go with a fast charge current of 800 milliamps. Again, it is just knowing that okay, this is how these calculations are done, right. So, R22 in our case 680 ohms determines the amount of fast charge current that you will get. Then there is the ISET 2. ISET 2 is pulled to ground because we are saying that no need to limit the current. Current limiting is anyway done at the source by, if you connect to a laptop will do the current limiting. This battery charging SOC does not need to do it. That is why ISET 2 is pulled to ground. Now, preterm you might remember the calculation we did there. So, R term is equal to K of preterm into percentage, right. K preterm was 200 ohm by percentage according to the data sheet, and then we want the charging to terminate at 10%. So, this is 2000 ohms, right. That is what R20 is. You can see that R20 is connected to ground through a 2 kilo ohm resistor. Now, we have two options for the temperature sensor. Now, in this case we are assuming, we are saying okay, if we are going with the 3 terminal battery, then let us connect the third terminal to pin 9 of this SOC, so that the temperature sensing function can be used. In cases where we do not want that temperature sensing function, suppose we have a variant of that product, we anyway have the provision to add a 10K resistor and take it to ground. So, this cross mark in red means do not populate, but the schematic has that flexibility. So, the layout will also have that slot for dropping the resistor if needed at a later point. So, it might be possible that you get one batch of batteries that come without the third wire. In those cases, what you would do is you would manufacture the PCBs in a way that that 10K resistor gets populated, right. So, in this case, the way you might want to understand it is okay, the TS function is driven by the third lead from the battery and this 10K does not come into picture. Then we have charging indicator, which, like I told you, the way this charging indicator does as per the data sheet is, it is what is called an open FET. You might, I do not know if you have been taught what a FET is, but you think of it like a switch with a connection to ground. So, it is almost like a switch of this sort. So, when it is charging, this switch is closed, so this node is pulled down. When charging is done, this switch is open, so essentially this node is also floating. Now, if you have VDD and you connect a pull up resistor, the pull up resistor will compete against the switch. If the switch is off, essentially there is no current flowing through the pull up resistor, which means this voltage will come to VDD. So, whenever that voltage goes to VDD, you know that charging is done, either charging is not happening or done, right. So, that is what the statement here says, that there is an internal pull up in the MCU. So, the MCU has a 20 kilo ohm pull up resistor. If the switch is off, that pull up resistor will ensure that that node goes high for any subsequent logic operation. There is a power good pin which is just connected to power good. It is available for the MCU to take some action if needed. And then there is the VBAT, again ignore the text, and then the VSS is connected to ground. So, this is how you would put together a schematic for the battery charger subsystem, right. So, this is a subsystem that now answers all of the questions that were of interest to us. We have determined what our fast charge current is, we have set it to 800 milliamp. We have determined what our termination current is. Termination current is now 10% of fast charge. So, if fast charge current is 800 milliamp, when the termination current or when the current through the charger current into the battery comes to 80 milliamp, termination, so battery charging indication will go, or charging done indication will go high. So, let me repeat that. What I meant was that when the termination percentage, or when the current through the charger comes to 10% of the fast charge current. Fast charge current we have set it to be 800 milliamp. The the termination percentage we have set it to be 10%. When we chose this resistors to be 2K, we are setting the charging termination percentage to be 10% of fast charge current. So, when the charging current comes to 80 milliamp, which is 10% of 800 milliamp, what will happen is that the charging subsystem will essentially turn off this the switch, which means that the charging done indication will go high. The pull up resistor on the MCU will make sure that the battery charge battery charge bar pin is pulled high. So, the MCU knows that okay, battery charge pin or battery charge pin went from low to high, which means that it went from charging to charging done, right. So, that covers the points of interest to us. What we also know is that this SOC choice meant that we have an SOC that has high voltage protection. So, you are protected against any input voltage transients up to 25 volt plus. Actually, in our case you can see that there is a 1 microfarad capacitor which is rated to 25 volt. We felt that 20 volt maybe is the peak transient we want to support, that drove our choice. The charger SOC is actually capable of sustaining even higher voltages. The charger SOC has both short circuit and RSET shorting protection. So, we know that this is now a very solid battery charger SOC. The point I had mentioned as a parameter that I really did not spend much time talking about is what is the price of this SOC, right. We did not really compare 3-4 options and say okay, this is 5 rupees, this is 15 rupees, this is 25 rupees, what should we go with. Now, you know, you think about the charging action, right. Charging is through the life cycle of the product, a user will probably charge the device maybe 500 times, 1000 times, right. Now, let us say one user can charge the device 1000 times. So, 1000 different, technically 1000 different ways in which a single user might be charging the device. If you have a million users, that is a 1000 million, a billion different ways in which the charging action can be done. So when you feel, oh okay, see, this is so central to the product, and there are maybe a billion different interactions that are going to happen with this subsystem for the user. So you would be inclined to take, and if charging doesn't work, or if I can't use this charger, I can't use that charger, as a user I will get irritated. So it is important, at least we make the call that okay, when it comes to the charging subsystem, it is important to say no, let's go with a system that is an SOC that is very well designed, that we can trust like crazy to take care of these billion different interactions that our collection of users will have with this subsystem, right? And this is again, some of these are judgment calls, right? This is not a, you can't say okay, this is how I will prove that this is more valuable than that. It is a judgment call, and somebody else might make a different judgment call, right? Somebody else might say no, I don't want to spend 25 rupees on the battery charger because my product is priced only at 800 rupees. So maybe I am going to go look for a 5 rupee charger. Nothing wrong with that way of thinking. Somewhere there is, you start from a price that the end customer is willing to pay for your product, and then from there you work your way down the bill of materials. And as long as you are able to sensibly correlate, yeah, I understand the limitations of my system, I know the reasons I am taking the decisions that I am taking, then you're, that's the best you can do anyway. So that is the charging subsystem, right? It's a 100% analog subsystem, and the kind of methodology we followed here is maybe the general methodology that is good to take in the context of being an embedded system engineer, where you want to be able to say that I am not building the SOC, I am a user of the SOC. Oh, even though I am a user of the SOC, working knowledge of that block is valuable to me, so that I am able to understand, oh okay, this is how this operates, this is the general principles with which this block is done. Then I say okay, that's I know the general principles now, I know what all I should worry about. Now if you give me the data sheet and maybe the application note, I can go through and I can see, I can now compare and contrast different offerings and decide what is best for my system, right? You are always going to be driven by performance, reliability, power, price, right? There are always the factors that come into play whatever SOC you are picking up, and a working knowledge of how that subsystem operates gives you immense power when it comes to evaluating those trade-offs. So anytime you are working with a subsystem, I would encourage you to sort of take the same approach, where you say okay, let me have a working knowledge of that subsystem. With that working knowledge, I am now ready to compare and contrast different offerings, so that I can then make a sensible judgment on what SOC to choose.